Hi everyone. From this module we learn the spectroscopic applications in inorganic chemistry. This is 4th semester's MSc Karnataka State Open University syllabus. From this unit, first we'll introduce that what is IR spectroscopy of inorganic compounds, the diatomic molecules of the type AB or A2, triatomic molecules of the type AB2 or ABC, tetraatomic molecules of the type AB3, pentamolecules of the type AB4, hexaatomic molecules of the type AB5, heptaatomic molecules of the type AB6, and we'll discuss IR spectral study of water, lattice water, aqua and hydroxyl complexes, lattice water, some important IR spectral study of sulfate and carbonate complexes, chelating, nitro complexes, applications in coordination chemistry, complexes of ethylene, diamine and related ligands, metal carbonyls, finally organometallic compounds. Here, the inorganic molecules are generally formed by the metal-ligand complexes. The metal-ligand bond vibrations are sensitive to nature of ligand and metal. During the formation of these complexes molecule, stretching vibrations, bending vibrations of this metal-ligand bond appears in the low frequency region due to also heavy mass of the metal atom or ion. The most common linkages in coordination compounds are metal oxygen, metal nitrogen, metal halogen, metal sulfur. In general, metal oxygen stretching vibrations gives a more intense and broad band than metal nitrogen stretching vibrations. This is because of this dipole moment changing taking place in metal oxygen bond than metal nitrogen bond. Anyhow, we know that the oxygen is more electronegative than that oxygen nitrogen. That's why the metal oxygen stretching vibrations gives more intense and broad band. Next we consider that metal sulfur stretching vibration is generally of weak to medium intensity. Vibrations occurs at lower frequencies related to metal oxygen and metal nitrogen stretching vibrations. The metal halogen stretching vibration is usually medium to strong in infrared spectrum. The vibrations such as metal sulfur, metal selenium, metal phosphor, metal carbon are expected to show only a slight change in dipole moment. Therefore, the vibrations would be of weak to medium intensity. Some important factors are responsible for affecting the metal-ligand vibrations. Higher the oxidation state of the metal, higher is the frequency of vibration. Greater the mass of the metal and ligand, lower is the frequency. Higher the coordination number of the metal, lower is the frequency. Greater the basicity of the ligand, the greater the frequency for sigma bonding. Non-bridging ligand have higher frequency than bridging ligand. Greater the size of counter ion, smaller is the frequency, and higher the ligand field stabilizing energy, higher the frequency of vibration. In this module, we learn the higher or infrared spectra of inorganic compound. So many inorganic compounds are taken as an example. Actually, the inorganic molecules of the type here AB, AB2 and A2B and AB4, AB6, AB7 molecules like that. If we consider AB2 molecules or A2B molecules are what here? H2, Cl2, O2, NO2. These are all what? A2 type of diatomic molecules. These are called homonuclear diatomic molecules. The vibrations of a homonuclear diatomic molecules like A2 is infrared inactive because here there is no any dipole moment. The dipole moment is 0. We are getting A2 is inactive molecule. The other examples of these diatomic molecules like that AB or CO, HCl, HBr. These are all called heteronuclear diatomic molecule. The heteronuclear diatomic molecules, it gives the intense peak because it shows the dipole moment value. This is the representations of this. These are the representations of this intense peak for that diatomic molecules of the type AB. Just we see that here, once these heteronuclear diatomic molecules like AB will necessarily have a permanent dipole moment because of asymmetry in its electron distribution, and the dipole moment occurs along the bond axis. The vibrations of the dipole moment with inner nuclear distance are represented here. These are all what here? Different wave number in that different stretchings of these diatomic inorganic molecules. For this, M means metal, that X means halogen. Metal hydrogen stretching appear at wave numbers like here 2000, 250 to 1700 per centimeter. The MH bending here appear at here 800 to 600. Here metal halogen stretching at here 750 to 100 per centimeter. The M double bond O stretching appear at here 1010 to 850 per centimeter, and metal nitrogen stretching appear this one. These are all what characteristics infrared bonds of diatomic inorganic molecules. Next we will see that triatomic molecules of the type here A2, AB2 or ABC. Generally the triatomic molecules are classified in the form of what? Either it is in AB2 or ABC or A2B type or also. Consider examples of these AB2 molecules like that. The familiar examples are CO2, NO2, SO2. These are all what coming under in AB2 type of electrolytes. No, sorry, AB2 type of molecules. Next we consider here O and Cl, HCN. These are all what ABC type of molecule. The triatomic molecules of the general formula here AB2 or ABC may have either a bent or linear structure. Generally, AB2 molecules, it gives a bent-in structure. ABC molecules, it gives a linear in structure. First, we have to look whether the molecule is linear or non-linear. In case of linear, then we have to look whether it is symmetrical or unsymmetrical. Symmetrical means here BAB form. Unsymmetrical means here that is BBA molecules. Consider examples of this symmetric molecules like that here. H2O molecule, SO2, NO2, ONCl. These are all examples of these bent triatomic molecules. Molecules such as CO2, CH2, HCN are linear triatomic molecules. Bent triatomic molecules have three normal modes of vibration. Two of the vibrations are stretching modes, remaining one is that bending mode. Here, once again, bent triatomic molecules have three normal modes of vibration. Two of the vibrations are stretching modes and the remaining one vibration is a bending mode. Here, this is what some representations of this AB2 type of molecule. Here, normal modes of vibrations of bent. Here, bent molecules. The direction perpendicular to the plane of the paper. That one. Each of the normal vibration of a bent triatomic molecule, there is change in the dipole moment of the molecule. Next we consider for this linear molecules. In that linear molecules, just you see, ABC type has four normal modes. For example, carbon dioxide molecule is typical. A B2 type molecules, the vibrations of carbon dioxide molecules are depicted in that figure. Here, observe frequencies are also indicated. The bending vibration shows in the plane of the paper and perpendicular it are to distinct normal vibrations, but they occur at same frequency. Such vibrations are said to be degenerate. Degenerate vibrations are found in molecules of higher symmetry. Next we consider another type of these molecules. Here this is also a ABC type of molecules. In this ABC type of molecules, the stretching vibration is termed as here N triple bond C stretching and other is CS stretching. These are all what? NCS molecule stretching vibrations. Here there is no dipole moment change during the symmetric stretching vibrations of a linear symmetric triatomic molecule such as carbon dioxide. These are all what? Characteristics, infrared bonds of triatomic inorganic molecules. For this linear, this is bent in structure. Next we'll move on to that tetraatomic molecules of the type AB3. In that tetraatomic molecules of the type AB3 possess either pyramidal or planar geometry. The normal modes of infrared active vibrations of planar and pyramidal AB3 molecules are illustrated in that figure. The infrared absorption bands of some planar and pyramidal tetraatomic molecules are given in table 3. Here, ligand may also adopt pyramidal and planar structures, and the nature of coordination also affect the resulting infrared bands of these ligands. This is what? Planar molecules like that BF3, calcium carbonate, potassium nitrate, sulfur trioxide. This is what? Pyramidal structures like that PF3 and sulfide, chloride and iodide molecules are mentioned here. This is pentatomic molecules of the type AB4, 5-atom pentatomic molecules of the type AB4, and ligands commonly adopt tetrahedral and square planar shapes. The normal modes of tetrahedral and square planar is AB4. The tetrahedral AB4 molecules show 2 infrared active normal modes of vibration, while the square planar AB4 molecules show 3 infrared active normal mode vibration. These are all the representations of this vibration, normal modes of vibrations of this tetrahedral. Is what tetrahedral molecules. This is what the square planar molecules. This is what square planar molecules. Okay. These are all the characteristics bonds of 5 atoms in inorganic molecules. For tetrahedral methane, it appears at vibration of frequencies here 3000, 19 and 1003, not 6. This is square planar complexes for that. In hexaatomic molecules of the type AB5, 6 atoms of the AB5 type have received considerable attention vibrational spectroscopy point of study. In AB5 molecule may adopt trigonal bipyramidal, square pyramidal and planar pentagonal structure. The trigonal bipyramidal have 6 normal infrared vibrations, while square planar pentagonal AB5 molecules show 3 infrared active normal vibrations. The normal mode of vibrations of an AB5 molecule in the trigonal bipyramidal and square pyramidal geometry are depicted in that figure 8 and 9. Just to see here, this is trigonal bipyramidal structure. Here 2 types of bonds are there. One is axial bond and another one is equatorial bond. Just we have to see that normal modes of vibrations of a trigonal bipyramidal AB5 molecule. This is what normal modes of vibrations of a square pyramidal AB5 molecule. And the next type of molecule is AB6. AB6 type of molecule invariably has an octahedral structure. A large number of inorganic compounds, particularly transition metal complex, comes under this category. The AB6 molecules means that is octahedral molecules show 15 normal modes of vibration, but only 2 of these infrared are active. These modes of vibrations of an octahedral AB6 molecules are illustrated in that figure. Okay, these are all what? Octahedral geometry, normal modes of vibrations of an octahedral molecule. This summarizes the infrared band of some hexahalo molecule which show an octahedral structure. The characteristic infrared band of octahedral inorganic molecules. Here Al F6 3-, Si F6 2-, vanadium hexafluoride and platinum hexafluoride. These are all what representative here what frequencies. Higher spectra study of lattice water and aquo and hydroxyl complexes. Actually, this is also expected question. For this, maximum inorganic salts are water binding capacity. Water in inorganic salts may be classified as lattice or coordinated water. There is, however, no definite border line between the two. The former term denotes water molecules trapped in the crystalline lattice, either by weak hydrogen bonds to the anion or by weak ionic bonds to the metal. The latter term denotes the water molecules bonded to the metal through partially covalent bond. Although bond distance and angles obtained from X-ray and neutron diffractions data provides direct information about the geometry of the water molecule in the lattice. Studies of vibrational spectra are also useful for this purpose. It should be noted, however, that the spectra of water molecules are highly sensitive to their surroundings. This is wagging, this is twisting, this is rocking. The three rotational modes of water in the solid state. Lattice water means lattice water absorb wave number in FTR 3350 to 3200 per centimeter in antisymmetric and symmetric OH stretching. 1630 to 1600 per centimeter hydrogen oxygen hydrogen bending. If the spectrum is examined under high resolution, the fine structure of these bands is observed. For example, calcium sulfate exhibit high peak, 8 peak. Its complete vibrational analysis can be made by factor group analysis. In the low frequency region, lattice water exhibit vibrational modes due to rotational oscillations of the water molecule. It is classified in three types depending on the directions of the principal axis of rotation. It should be noted, however, that these vibrational modes couple not only among themselves but also with internal modes of water and other ions in the crystals. That aqua complexes or water complexes, in addition to the three fundamental modes of free water molecule, coordinated water exhibit other modes. Vibrational spectroscopy is very useful in elucidating the structures of aqua complexes. For example, trichlorotitanium water should be formulated as trans, since it exhibits one titanium oxide stretching and one titanium chloride stretching mode. The chain gain showed infrared and Raman studies that structures of tetrahydrates and dehydrates resulting from the dehydration of manganese nitrate as follows. Next, spectral study of sulfate and carbonate. The free sulfate ion belongs to high symmetric point group TD. Other four fundamentals only frequency 3 and 4 are infrared active. If the symmetry of the ion is lowered by complex formation, the degenerate vibration split and Raman active modes appear in the infrared spectrum. These are all what? Some examples of these sulfato complexes. This is carbonato complexes. Unidentate and bidentate coordinations shown below are found in the majority of the carbonato complexes. These are all different complex appear. That's why it gives the different stretching vibrations, different bending vibrations are there. The basic salt, the OH stretching increasing along the following order. The basic salt is less than the carbonato complex, than acid or organic carbonate. This is the mono and multinuclear carbonyl compounds. In mononuclear, pentacarbonyl can exist both in square pyramidal and trigonal bipyramidal geometry, performing infrared spectra after calculating the IR active and Raman active bonds. This is the CO stretching in representative metal carbonyls. The carbon monoxide, free carbon monoxide. What we are getting here, 2150 per centimeter. MnCO6, that is cation. Chromium hexacarbonate, 2000 per centimeter. Vanadium, etc. Generally, it is used to distinguish the terminal and bridging carbonyl groups. The CO bonding in terminal carbonyl group is stronger than the bridging carbonyl group. Therefore, it is possible to differentiate the terminal carbonyl weight absorbed in the region of 2050 to 1900 per centimeter. The change in intensity of band is related to carbonyl group, can provide information for kinetic studies of the substitutions reactions involving replacement of carbonyls. This position is indicating that what in this region terminal carbonyl in this position is representations of this bridging carbonyl group in that complexes. In diketonated complexes, here beta diketones or 1,3 diketones bear two carbonyl groups that are separated by one carbon atoms. The carbon atom is the alpha carbon. In most beta diketones, the substituents on the alpha carbon or dihydrogen atom, substituent on the carbonyl functions can be an alkyl group, a fluorinating alkyl group, an aromatic or heteroaromatic group. The simplest beta ketone is the acetyl acetone, where the substituents on both carbonyl groups are methyl group. All other beta diketones can be considered as derived from this acetyl acetone and substitutions of CH3 groups. These are all representation. Here there is having only one CH3 groups are there. Here CH2, CH3 groups is attached. This is one more. This is what the structures of beta ketones with aliphatic substituents. This keto-enol equilibrium in acetyl acetone. The three main types of beta ketone complexes with metal ions have found. They are tris complexes. The Lewis base adducts of the tris complexes and tetra-tris complexes. These higher spectra of nitro and nitrito complexes. Many ligands are ambidentate. Ambidentate ligand means in that ligand molecule both the atoms donates the lone pair of electrons to the central metal atom. That is what ambidentate ligand. The meaning they have ability to bond a central atom in more than one way. Consider the thiocyanate. We can coordinate the via of these both nitrogen and sulfur atoms. Consider that NO2 molecules which can coordinate the via nitrogen or oxygen atom. The NO2 ligand can form a coordination complex with cobalt to the nitrogen atom or oxygen atom to yield two structural isomers. One is that nitrito and another one is nitro. When this central metal atom is directly attached to the nitrogen, that is nitro complexes, that oxygen is attached to the central metal atoms like cobalt to formation of these nitrito complexes. Once this metal and nitrogen bonding in that central metal complexes, it changes its frequency range. In case of metal and nitrogen, the vibrational frequency is 1450 to 1370. In that metal oxygen, what is that in nitrito complex is that vibrational frequency is in between the 1480 to 1380 per centimeter. Next we will move on to that chelating nitrito complexes. When the central metal atom is having different oxidation states, that is combined with that different ligating atom in that nitrito group will be shifted to a lower frequency to higher frequency. The separation between these two modes becomes much smaller than those of these unidentate complexes. It should be noted that the delta value depends on that degrees of asymmetry of the coordinated nitrito complex or group. It is expected that delta value is the smallest when the two NO bonds are equivalent and increases the degrees of asymmetric increases. We can record it is possible in that IR spectrum for this Nitro complex for several days later. The spectrum nearly identical to the Nitro complex. This is explained by the natural degradations of the kinetic product Nitro into the thermodynamically stable product Nitro. The next complex is thiocyanate complexes. In this thiocyanate complex, many of the associated groups, frequencies, can be used diagnostically for characterization. The structure and orientation of the ions are complex, both as an isolated entity or within a crystal lattice. The important factors that affect the appearance and nature of the infrared spectrum are hydration of compounds has a large effect on the spectrum, often adds a lot of complexity in the form of additional absorption bonds and structures to existing band. In that table, we provide that the group of frequencies and the functional group assignment are mentioned here. Consider that the carbonate ion of the frequency is in between 1490 to 1410 per centimeter. The following sulfate ions is in the range of 1130 to 1080. The nitrate ion, phosphate ion, silicate ions, ammonium ions, cyanide ions, thiocyanate ions and related ions are mentioned in that tabulated. What are the applications of this coordination chemistry from this IR spectroscopy? That metal complex or chelates are largely covalent in nature. The spectra of such compounds are dominated by the contributions of the ligand and its coordination chemistry. The ligands will be small species such as water or alumino molecules, or large complex species such as carbonyls. The complexes of ethylene diamine with related ligands, it shows different vibrational frequencies. Consider the chelating ethylene diamine. It is a very good chelating ligand. Simply it is called what? ADTA. It is in that 8 different conformations are probable. Consider the simple examples like that here, Gauche form and cis form. That is what? Gauche form, that is what? Cis form. Just we see that these are different molecules. We are getting different structural rotational isomers of this 1, 2 disubstituted ethane molecule. This is the bridging ethylene diamine molecule. The complexes of polyamines molecules like that, diethylene trimine, triamino triethylamine, triethylene tetramine. These are all what? Different ligands molecules which donates the more than one lone pair of electrons to central metal atoms to formation of a complex molecule. These are all different structures. These are different stereoisomers of this cobalt, amines chlorides molecule. This is ethylene diamine diene, the cobalt chloride 2+ ions. Generally, these type of complexes is stereologically changes. Once this molecule it undergoes stereologically changes, the vibrational frequency appears in different infrared spectra of this beta, beta dash, beta double dash of this triamino triethylamine complex with cobalt, and any lanthanides gives 3 isomers molecule. For example, IR spectra of this metal triamino triethylamines, whereas trienes molecule exist in that acido-anions molecule. These compounds give 3 isomers that can be distinguished by the CH2 rocking vibrations appear in that 920 to 869 per centimeter regions. These are all different IR peaks are mentioned here. Now we are going to study with that isomerism complexes. The meaning of isomerism means the compounds are having same molecular formula but different structural formula. That is what isomerism. The coordination compound it gives different isomers like that coordinate isomerism, linkage isomerism, hydrate isomerism. These are all what different types of this isomerism are mentioned here. Once this molecule it undergo different hybridization, it gives different wave numbers or different frequencies. The vibrational frequencies range of thiocyanate group with various bonding modes like that metal is directly attached to the nitrogen, metal is directly attached to the sulfur, metal is in between, the ligand is in between both nitrogen and sulfur are mentioned here. These are all what? Mode of coordination, frequencies, range we mentioned here. These are all representations of this 4 infrared spectra of this trans and cis twin chloride molecule. The metal carbonyls. Next concept, metal carbonyls. The infrared spectroscopy or IR spectroscopy can be readily used to distinguish types of bonding in metal carbonyls. A useful bond in the infrared spectra of carbonyl ligands in metal complexes is due to the CO stretching, which gives very strong sharp bands. The strength of bonding between d orbitals, the metal into pi star anti-bonding orbitals of the CO bond ligand determines the bond position. This is once the electron transfer into that carbonyl group to formation of the metal carbonyl molecules exist in the different regions. In that organometallic compounds, the hydrocarbon is react with that metals to formation of these organometallic compounds contain ligands directly bond to metal atoms or ions through carbon band. The metal carbon stretching wave numbers of organometallic compounds are observed in the 600 to 400 per centimeter range. Lighter the metals show band at higher values, The CH3 bending bands arises from metal CH3 group. The aromatic organometallic molecules show strong band near 1430 per centimeter. Due to benzene ring stretching, the metals directly attached to the benzene ring. Now I am going to summarize this unit. The infrared spectroscopy is used to study of vibrational motions of molecules. Studying of this transition can sometimes allows to determine what kind of atoms are bonded or grouped in an unknown compound. The stretching involves rhythmical displacement along the bond axis, such as the interatomic distance alternately increase or decreases. The one important condition is that only those vibrations that produce a change in electrical dipole moment of the molecule will be observed in the infrared spectrum. For example, the stretching vibrations in homonuclear diatomic molecules do not produce any change in dipole moment, and hence these molecules do not give rise to an IR spectrum. On the other hand, the CO, IB or produce IR spectra because these molecules contains a permanent dipole moment that will change as the bond is stretched or compressed. Here carbon dioxide is a linear molecule that does not have a permanent electric dipole. The spectrum of the two CO bonds can stretch in an asymmetric fashion and also bend to produce changes in the dipole moment. Thank you.